Howdy, and welcome to the session, Animated Execution Plans for Visual Learners. I am so glad you're here, virtually here at Virtual Summit, and I'm really excited to share some really nerdy database stuff, animated algorithms and whatnot. First, some mandatory slides. Okay, PASS has free stuff, and this free stuff is actually good. Check it out. Also, session evaluations. These really matter to me. I'm not that experienced of a speaker, so I really value feedback. I'm just a recording right now, so if I'm super boring and you decide to walk out on me, not gonna hurt my feelings. But I think databases are really cool, not boring. So if you see any way that I could do a better job of explaining, please let me know. Session evaluations. Some stuff about me. I'm not SQL famous. Who cares? I have a job where I work on performance issues for SQL Server. I'm a nerd, really. I'm a nerd. Who cares? Let's get to the stuff. Okay, you've probably seen this before working with SQL Server. It's an execution plan. You may remember what it was like as a junior DBA seeing an execution plan. Yeah, all these symbols and arrows, and I don't even know, do you read it right to left, left to right? I have had the privilege of interacting with some of the brightest SQL Server people out there, and I recognized they had something I didn't, which was a deep understanding of what was actually going on for each of those pictures in an execution plan. And what eventually enabled me to really grow was cutting out pieces of paper, shuffling them around to learn the algorithms myself. I highly recommend doing this yourself. In fact, if you can kind of just, well, I'm not going to see if you grab a piece of paper and cut it up and try to do everything while watching. Go for it. It's one of the best ways to learn. And my animations are kind of an attempt to share that intuition with you. Now, there are a lot of operators, a lot more than on this screen, and they're not just pictures, they mean something. And when you start to understand what they mean, that's the difference between a good and a great query plan tuner. Let me start with a warning. This stuff can get pretty complicated, so I'm going to be oversimplifying. If you hear me say something and you think, but there's an edge case. Yeah, there are a lot of edge cases. There are a lot of things I'm going to be covering up, going fast through, just because I don't have time for all the detail. The detail's really cool, and I highly recommend it. But this is the simplified version. Okay, let's start with very basics. Please bear with me. I hope you're aware, but we'll take a running start. We're going to talk about seek and scan. And it really comes down to this basic idea that organized data is easier to search. And one of the most common ways to organize data in SQL Server is this structure called a B tree. Obviously called a B tree because it looks like a tree. Kind of. That's better. Okay. Functionally, those top pages are used for navigating, and the bottom pages contain all of the data. There are names for them that correspond to the parts of a tree. That top one is the root node or root page. The bottom ones are the leaf pages. The ones in between are, no, they're not branch pages. They're called non-leaf pages. Computer science terminology, don't ask me. Now, a seek is navigating through this B-tree structure to find data you're looking for. A scan is when you start at the beginning and just keep reading. You can visualize them kind of like this. But I have a question for you. What about this operation? If you use the B-tree to find a specific starting point and then keep reading, what is this? Well, if you're reading an execution plan, this will show up as a seek. Perhaps a more technical name for it would be a range scan, which you can actually see in some of the DMVs. Some example queries that would produce a seek or a scan. That one on the left, select where, and then I'm selecting based off of the primary key of that table, just getting one row. That's a seek. Select star from table, surprise, not really. It's a scan. And remember that a clustered index is the table, but sometimes that clustered index isn't organized in a way that makes it really easy to search on what you're looking for. It might be arranged according to ID, but pretty often you're searching for people's names. In that case, you can build a non-clustered index, which is usually a subset of the data ordered in a different way, and that lives as a separate B-tree structure containing pointers, which would be the primary key, technically clustering key, containing that which allows you to go back to the clustered index to find any other info you need. Now we can actually get into execution plans. And I want to start with some common operators. Why not start at the top? Let's look at the top operator. The top operator only passes through a certain number of rows. In this case, here's an example query. Select top one from person.person. If we were to look at an execution plan for that, we see the top operator. It will only, in this case, pass through one row. I have a question for you, though. We see a scan in there. How many rows is that scan going to read? The answer is just one row. If that surprises you, the explanation is that execution plans suck. No, I don't mean it that way. I love execution plans. Here's what I mean. Starting at the select, rows are requested. They're pulled. They're sucked up the execution plan. Let me just give you an animation. This is how I visualize it. Rows are pulled from the left. Each operator requests a row from its child or children, and then the actual data is passed right to left. A funny story about this animation, I showed it to a friend and he told me, operators don't say please. This is a demand-based model, not a request model. It's too good not to change the animation. Okay, filter operator is next. And what this one does is it only passes through the rows that actually meet whatever condition is being filtered on. You can see it here as a separate operator, and here's how I visualize it. It examines each row it gets, checks the conditions. If the row fails, well, it just discards it and asks for the next one. But if that row passes whatever conditions, it's checking, it just passes it up the chain of the execution plan. Another really common operator is sort, and you usually see this with an order by. Some other situations as well. Now, there's something really interesting about the sort operator. It's a blocking operator. What's going on is with a sort, it has to read all of the rows before it can return any row. And if you were sneaky and grabbed some pieces of paper, you might be able to figure this out. If you check your stack of numbers, flip it over and shuffle them up, and then I tell you, hey, find the largest number in there. You can't just grab the top one and say, aha, it's it. You can't even go through that stack of numbers until you're almost done, because what if that last paper contains the largest row, the largest number? The sort has to read everything before it can start passing along rows. That's what makes this a blocking operator. Also leads to some funny situations. I had an Azure database once that the devs started asking, hey, we're getting reports that it's not usable. What's going on? Well, an intern was running a query, and that query just kind of was a really expensive query. And yeah, I talked to the intern. He's like, I don't understand. Like, I was only asking for 100 rows. Why was it an expensive query? It was because of the order by. So his query had to do a lot of complicated expressions on the entire table, even though he was asking for 100 rows. Sort has to read everything before it can return anything. So this is just a handful of operators so far, but it's already enough to see some really interesting stuff shake out of queries and query plans. So what I'm going to do is I'm going to make a copy of the users table from the Stack Overflow database, and I'm going to add some indexes to it. We have the primary key, which is the clustering key for this table on ID, and then I've added non-clustered indexes on display name, creation date, and reputation. Let's see if you can figure out what kind of query plans we're going to get. First query, select star from table. Oh, big mystery. It's a clustered index scan. Hopefully no surprise. What if we specify ID, where ID equals some number? Well, in this case, we get a clustered index seek. Good. What about this? Select creation date from users demo. Oh yes, we do get a scan, but notice the type of scan that this is. It's not a clustered index scan. It's just an index scan. The reason is that non-clustered index on creation date doesn't contain all the columns. So it's actually a lot smaller and a lot faster to just read through. And that's why SQL Server scans that instead of the clustered index. But what about this scenario? What if I add the column ID to that query? What's going to happen? Am I still going to get a non-clustered index scan, or does it have to be the clustered index that gets scanned? Well, it's still just the index scan. And you might remember me mentioning for non-clustered indexes that they need a pointer, and that pointer is the clustering key. It's baked into that non-clustered index. No need to go to the clustered index for it in this case. Okay, here's a query with a where, and it's not on an indexed column, and we see the filter operator show up. Pretty cool. Okay. What about this query? Will we also get a filter for this one? The fact that I'm asking should be a clue. There's no filter. Where did it go? Well, if you were to mouse over that scan, you would see a predicate in it. What's happening is something called predicate pushdown. Passing rows to a separate filter operator is actually a bit more expensive than just checking them as you're reading them. I think this was introduced in SQL 2008, and there's a decent speed boost. If you know there's a filter going on, a where condition, and you don't see the filter operator, this is probably what's happening. Also, the fact that we do see a filter operator can be a sign that there is maybe a little bit of something to investigate. The reason we saw it earlier, here, about me is a max length column. We can also see the filter operator when the expression is complexed. So here I have upvotes is divisible by 5, no filter. But if I have a where clause that's really complicated, there's where the filter shows up again. If you see a filter, check it. All right, what kind of query plan will we get for this query? We have an order by. Also, that downvotes column, not indexed. Here's where we see a sort. What about the reputation column? What query plan do we get here? Notice that there's an index on it. No sort needed. And that's because the non-clustered index is already sorted based off of reputation. That's how the B tree works. What if we add in a top 1 and then order by descending? Will that mess up SQL Server? No. It just adds in a top, and then even though it's reading descending, that doesn't matter. SQL Server can read an index backwards. What about upvotes ordered descending? Notice there's no index here. So we're probably going to get a sort and a top, but we actually see something new and different, which is a combination of the two, the top and sort. And something interesting about the top and sort is that there are actually multiple algorithms for it. Here are 2 actual execution plans for the top and sort. And notice that 101 is more than twice the time of a top 100. The reason is that for 100 and less in a top and sort, SQL Server is only holding on to that many rows at a time and keeping the largest or smallest, the top that it's found while it reads through everything. As soon as you go to 101 though, it does it a different way, which is it sorts all the rows and then reads the first 101 in this case. Now is usually the point when I check to see just how many audience members are falling asleep. But like I've mentioned, I'm only a recording right now, so I get to pretend that none of you are, and that you're actually excited to see the next section, which is on joins, my favorite. Let's dive in. Now, the join that you write as part of a SQL query is actually a logical join. Inner join, outer join, cross join. And that's different from what SQL Server has to do in actually comparing the data in the two tables. The algorithms used to compare data are called physical joins, and there are 3 of them. Probably the simplest would be the nested loops join. It's called nested loops because if you wrote it out in code, it would pretty much be one for loop nested inside of another. And the way it works is, well, imagine you have these stacks of numbers again. You take the top one from the first pile and you look through all of the second pile for any matches. Then you take the second, you look at all of the numbers, and so on. And I have an animation for this just in case words aren't doing it for you. So that top table or input is called the outer table, and then the bottom one is called the inner table, representing what part of the loops in code they would be. And if you stare at this algorithm for a while, you might notice its weakness, which is it does a lot of repeat work. It reads all those values on that bottom or inner side multiple times. Would you really want to stick around and watch me animate this? It'd take forever. So nested loops, it works really well with small inputs, but it can just explode runtime if you have really large inner inputs. Some common patterns that you'll see with nested loops, you'll often see a seek on that bottom or inner side, and the reason for that is if there's a supporting index, why read the entire table? Why not just look directly and see if you can find a match? Much faster that way. And similarly, you'll see key lookups with nested loops. Now, a key lookup is a seek. Specifically, it's a seek on the clustered index of a table where the outer table is an index, is a non-clustered index on that same table. Okay. What if we don't like repeating work? What if we only want to read each table one time? Well, there's an algorithm for that. Merge. And the idea with merge is that each input is sorted. So imagine we have our stacks of numbers again, and we take the top one from each, and we kind of compare, oh, this one's smaller, this one's larger, and we kind of work our way through the stacks of paper, comparing as we go. Let's just look at an animation. So notice each input is sorted, and it just works its way through looking for the matches. There's something else that I want you to notice with this. I have repeated values here, but I only have repeated values for that bottom input. The algorithm for a merge join, if you have repeated values in both, has to involve like a little bit of rewinding and checking, and gets a lot more complicated. I have an animation of it here, but it's just a little bit annoying to explain, and it does hurt performance. Watch out for this situation, which is called a many-to-many merge join. So merge, it's really fast, but it's only really fast if you already have your inputs sorted and you're avoiding the many-to-many scenario. So maybe we can use an algorithm that only reads each input once and doesn't have to care about sorted data. Sounds like it would be perfect, right? Well, we get the hash join, and that's what it does. There are 2 phases to it, and you know what? Let me just dive into the animation and I'll explain as you can stare at the pretty pictures. First, though, a note about my fake hash algorithm. What I do is I just spell out the number I get, and I take the first letter. That's my fake hash. Okay, so there are two phases to this. We start with that top input, which will be called the build table. And we hash each of those values and put them into a hash table. Now, realistically, that's not what a hash table looks like, and that's not how a hash table works. Oh well. After the hash table is built, that probe side, the bottom input is probed. Each value is, again, hashed and then compared to what exists in the hash table. Okay, so again, we start with the build phase, building the hash table off of that top input. Then we move to the probe phase, looking for matches based off of that hash in the hash table. Okay. Can you spot the weakness, however, of the hash join? It looks good, like it only needs to read each input once, and it doesn't require sorted data, but where does that hash table have to live? It has to live in memory. And if you don't have enough memory, you end up with something that's called a spill. And I've even animated that for you. So imagine as you're building your hash tables, looking at that build input, you run out of memory. What do? You take part of what you've built and you write it to disk. In SQL Server case, you write it to tempdb. Then you continue as normal, but any probe values that would land in that partition, you write to tempdb also. After you're done, you just start over with what's in tempdb. Now, I keep saying write to disk. Writing to disk is slow. And if you have a hash join that spills, it's probably slow. You don't want this. So, no operator is perfect. Key features of the hash join. It's semi-blocking. That first part, that build part of the algorithm, needs to read all of its input before it can start returning rows from the probe side. Also, hash join requires memory. So which join is best? Well, it really depends. I'm sure you've never heard that before. If I had to summarize it, it would look something like this. The nested loops is what you're going to see most often in an OLTP environment. Just a handful of rows, plenty of indexes. Merge join, if you already have sorted inputs, it's probably going to be the fastest. But how often do you end up with a join key that's sorted exactly the way you want it on both tables? It's not too common. Hash is generally fast, but you have to watch out for that memory usage, and you know it really could be a sign that you're missing some indexes. If you only want a couple of rows, why do a hash join when some indexes would allow you to do a nested loops instead? Now, I'm moving to aggregates now, because even though we're back to just looking at, well, in our case, one table at a time, the algorithms involved are actually very similar to the merge and the hash. So what I'm working off of is a count and a group by example. Let's start with the stream aggregate. The stream is very similar to the merge join. It requires sorted data, and as it reads through, it can return information as soon as it's done with one of those groups. So it's not a blocking operator, it's a streaming operator, stream aggregate. Very similar to the hash join is the hash aggregate. What this one does is it takes that input, it builds a hash table, and accumulates whatever you're tracking. Now, just like the hash join, there's blocking involved. It can't return any rows until it's done reading the input. It doesn't need to be sorted, and it does require memory, which means it also can spill. One of my favorite things to do is make SQL Server bend to my will. And you can force SQL Server to use a particular join type, and you can nudge it in particular directions. However, you really should be careful about it. For an example, when you are looking at a join, you can specify the join type by adding in that keyword loop, merge, or hash in between. So in this case, I can write inner hash join, and I will get a hash join. But I'm also going to get something else if I do it this way. You can look at the messages and you'll see a warning. The join order has been enforced. All right? If you force a join using this method, the tables will occur in the order that you write them in the query. That can cause problems. Probably a better way to do it would be with the option section. And I can write option loop join. And what that does is throughout the entire query, SQL Server is only allowed to consider loop joins. There are multiple things you can do, such as you can write option loop join hash join, and that allows SQL Server to consider only loop joins or hash joins, excluding merges. You can't quite force SQL Server to only use one type of aggregate. It will ignore you in certain situations, but you can definitely nudge it in that direction. And the way you do that is with the order group or the hash group commands in option. Of course, there is the nuclear option for forcing SQL Server to do what you want, which is the use plan hint. The way you do that is you take the XML of the execution plan shape that you want and you paste it in there. And you make sure to remove apostrophes and you watch out for other pitfalls. But you can more or less force SQL Server to use what you want it to. But again, let me give you a word of caution with this. Be very careful if you're doing it in production. Just because one join was faster than another for your particular customer ID, for your particular procedure, doesn't mean it should always be used. And be very careful leaving it around. Who knows if that's still the best a year from now. I might as well take this time to go over a pet peeve of mine. You might have noticed in the execution plans I've been showing, and whatever you look at yourself, this cost percentage number. Do you know what that is? I'll tell you what that is. It's garbage, junk, practically worthless. At least it probably doesn't mean what you've been told it means. I see a lot of misinformation about this. That is nothing to do with actual performance of a query. What it has to do is it's something from the optimization process left over. And I really want to prove to you that you can't trust it. Here I have two identical tables. All I had to do to get different percentage numbers was screw with the statistics. You can see each of them, one row, each of them too fast to measure at 0 seconds. And yet, one query SQL Server thinks will be 19% and the other 81%. It's wrong. Here's another fun wrong example. What do those percentage numbers add up to? Notice this is an actual plan as well. We read one row from A, we read 0 rows from B, and they both show up as costing 100%. Yeah, this isn't accurate. Here's another contrived example. Okay, I'm going to do some XML operations, but I'm doing it on a stupidly simple XML. Which query do you think SQL Server is going to count as the expensive one? Which one do you think is actually going to take a lot of effort? Here are actual plans. Notice that top XML query, too fast to measure, 0 seconds. Counting millions of rows, well, that takes a second. Which is like, what? Is that infinity times faster than 0? But SQL Server calls that first one 74% query cost, that bottom one 26% query cost. You can see other really funny stuff if you're looking at estimated plans with an if. Yeah, 261,000%. What's going on with these? As part of the query optimization process, SQL Server has to figure out whether one possible plan might or might not be better than another. And so it assigns arbitrary points. You've often heard these called query bucks. It assigns points to various operations and various queries to help it decide what to do. And it leaves these hanging around even in actual execution plans. Sometimes they happen to be accurate. SQL Server knows that reading millions of rows is a lot more effort than reading one row. But these are only estimates based off of what SQL Server knows about the statistics of the table. When you're tuning query plans, in the real world, oftentimes the query plan you're looking at has gone wrong because SQL Server had bad statistics. It's really common to find that the actual most expensive operator was just costed at a couple percent in the plan. So, when somebody asks you what that cost percentage is, you know what to tell them. It's junk. Now I have what I hope will be some helpful animations of actual execution plans. Let's take a look. Here we have just the nested loops and how I visualize it. It's streaming, and in this case with a seek on the bottom side, we take that row from the top, we search for the match in the bottom, and then we pass it on up. If we had a scan on that inner side of a nested loop, well, each row from the top or outer table has to then be matched to multiple, or probably all, of the rows of the scan on the inner side. This is how I would visualize that. With a merge join, again, it looks approximately even, reading from both. A merge join doesn't always have both inputs immediately sorted, so you might see a sort operator. And this is how I visualize that. With that first row for the scan, it reaches the merge join. It goes to pull a row from the bottom scan, but that sort has to read all the rows first, and then it can start feeding those rows to the merge join. This is, I think, a really helpful animation in seeing how sort is a blocking operator. All right. Here's how I visualize a hash join. So notice it reads all the rows from that top input, the build input first. It builds the hash table. Then, once it's into the probe phase, it can start passing those rows on to the client, the select. Here's a more complicated query. So what will happen is a row gets fed to the nested loops. The loops wants to pull rows from the hash match, but that hash join can't return any rows until it has built the hash table and can start probing. That inner operation will be repeated for every row coming out of that top scan. Remember, nested loops repeats work. Be very wary. I had to do a lot of work to get this plan shape. Okay, here we have an example of a key lookup plan. What's going on here is we're searching for all the people whose last name starts with Z. And there's an index on last name, so we can efficiently seek through the last names beginning with Z. But because I say select star, there are some columns not included in that index. We have to go back to the main table to get that data requested. And that's the key lookup. Okay, so we're seeking, and then we're seeking again with that key lookup for this query. But what happens when I'm looking for the last names that begin with M? Well, there are a lot more last names that begin with M, and we end up with this plan, just a scan. SQL Server decides that, it's actually faster to just read through the table once instead of for each of those lots of names beginning with M, making a separate trip back to the table and going back and forth, back and forth. This is also known as the tipping point problem. Sometimes SQL Server decides, I'm not doing all those key lookups, I'm just doing a scan. Here's an example I came up with where we would see a merge join, and the reason for that is the clustering keys for both of these tables are ordered on business entity ID. So selecting from a join here, we see a natural merge. Here's something interesting though. If I specify a particular business entity ID, we move to a nested loop. Well, there's no reason to read through everything. We have a value and we can use a seek on both. The nested loop ends up much faster. Here's a place where you might see a hash join. And there's also something to think about that's really interesting. That phone number type table, it only has 3 rows. So notice what SQL Server does. It builds the hash table from that table and not the other ones. And maybe if you spend a while, you could figure out why that is. if you're building a hash table, having a small number of values means you only need a small amount of memory. It's going to be a lot faster. So SQL Server normally picks what it thinks is the smaller table to do a hash join with, to use as the build side in a hash join. Okay. What will happen if I add a top 1 to this query? Will I still get a hash join? No, I actually go to nested loops. Similar reason, it's only a small amount of data. We don't need all of it. We just end up with a scan and a seek. Here's an example that I think is really fun. Okay, let's start with a query that's a little bit complex, so take some time to look at it and understand it. We're selecting some information from the person.person table, but I'm using a cross apply here, and the cross apply is a for every row operation. So for every row from the person table, select the count of rows from the address table. Okay. Now, you might think of this plan for it. All right. So we start at the top for the index scan, and then for each row coming out of there, we would scan the address table, get the count of rows, and finish the query. Thankfully, this is not the plan that SQL Server actually chooses. SQL Server isn't stupid most of the time. Instead, the way SQL Server builds an execution plan for this query is like this. What it does is it counts the number of rows in the address table just once, and then it reads all the rows from person. A lot smarter. And in fact, we can see the time difference. It took 36 seconds to run this plan and 5 milliseconds to run this. Now we can do something interesting with this query. We can use option force order. And what that does is it requires the person table to be first, or on that top part of the execution plan. And the plan we get has something really interesting. It has a spool. And basically what a spool is just a way to store and later reuse results. The way I visualize it is like this. After that first row from the scan comes in, that scan on the bottom, the address, feeds into the stream aggregate. We get that count of rows, and then we store it in that table spool. Then the nested loop can continue reading rows from the scan on person into the table spool, just containing the count. I had to do a little bit of work in order to get the really bad plan. I had to force order, and I had to specify no performance spool, and because SQL Server knew just how much work would be involved, I had to tell it to only use a serial plan with that max.1 hint. Don't do this. I am abusing SQL Server. Do not do this in production. Do this in dev and enjoy it. There's something else interesting that can happen. What if I add in option hash join? I actually get an error message. The reason for this is that hash join and merge join actually require a join condition on an equality. You think about it, you can't produce a hash of greater than 2017, you have to be joining on a match. Like a hash join checks for a match. I have another demo that I enjoy, this one dealing with aggregates. Again, I'm going to use a table from the Stack Overflow database, and I only have a non-clustered index on the score column. What happens if we have an aggregate query on an indexed column versus a column that doesn't have an index? In this case, I'm looking for select score and count, group by score, versus select answer count, count, group by answer count. Score has an index to support it, answer count does not. What kind of query plans are we going to get? Well, this is where we see the stream aggregate versus the hash aggregate. Because score has an index on it, that index is already sorted and can easily work with the stream aggregate algorithm. And we can also see for almost 4 million rows, it takes about half a second. However, with the hash aggregate working on the same almost 4 million rows, it takes almost 12 seconds. We can also see something interesting just in the rows returned. Remember how stream aggregate works on sorted data? It still outputs sorted data. And if we look at the scores and the totals, we see that score is still in order. The output of the hash match, on the other hand, is in kind of a random order. It is not sorted because that's the way the hash match works. So what happens when we force a stream aggregate? Well, we need the sort operator. Remember that stream aggregate only works on sorted data. It has to be sorted somehow, and because that's almost 4 million rows, that sort happens to spill. And this ends up as slow. That's a lot slower than under half a second. If you want to practice this yourself and really get better, there are some things that I've done that I can highly recommend. Basically, find a test installation of SQL Server, get a database, probably Stack Overflow or one of its variants just for the size of data, and see if you can get execution plans with various operators in them. Start just by trying to naturally generate each of the 3 physical join types. Then kind of branch out. See if you can find a query plan where scanning is faster than seeking. Work on queries for the aggregates. Do stuff similar to what I just did in that last demo. And who knows, maybe if you want to get really advanced, see what kind of spools you can find. But what I really recommend, like if you are a nerd and if you resonate with the nerdy awesomeness that is the algorithms here, cut out pieces of paper, slide them around on your desk, figuring out actually how to do it yourself. You will learn and you will grow from that. Thanks for putting up with me. I hope I didn't put too many of you to sleep. Enjoy Virtual Pass. Ciao. I'm going to be in chat answering questions, trying to answer questions. Oh, am I making it hard on my future me? But yeah, I'm going to make it hard on future me. Future me is going to be answering your hardest questions. Go ahead, throw it in. Doesn't cost me anything right now. Have fun.